Yeah, let's wait for a couple of minutes and then we will start. Okay. Hello, everyone. Yeah. So, okay. Uh, yeah. So let's start today's discussion. Uh, all right. So last time we saw uh, eigenvalues as eigenvectors. In the last session, we talked about diagonalization of a matrix. Okay. So in today's discussion, we will see. Uh, yeah. So in today's discussion, we will continue our discussion on diagonalization. And yeah, and we will prove a theorem which says that any matrix for a given matrix representation there exists a basis that can be converted. There exists a basis so that with respect to that basis the matrix representation or the operator has a upper triangular matrix representation. Okay, so let's start with an example. So consider this matrix. Okay, so first row is 100, second row is 110, and third row is 003. Clearly, since it's an upper triangular it's a lower triangular matrix. So the eigenvalues are 113. Okay. Now we can calculate for each of the eigenvalue what is the eigenvector. So for eigenvalue lambda equal to 1, the eigenvector we calculate by calculating the null space of A minus lambda I, where lambda is 1. So we need to calculate the null space of A minus I. Null space of A minus I is basically calculating the null space of this matrix. Now what is this matrix? What is the nullity of this matrix? Can anyone tell? Nullity of this matrix?
X plus 2y. X plus 2y is equal to 0.
X plus 2y is equal to 0. No, x equal
So,
to 0
so
and 2y is equal to
2z,
0.
2z,
2z
x plus
equal to
2z.
0. Not x plus 2z. X equal to 0 and 2z equal to 0.
Am I right? X plus 2z is.
Not x plus 2z. I'm saying x equal to 0 and 2z equal to 0.
Yeah.
Right? So y
Okay,
can be
okay,
anything.
yeah. Okay, so x is equal to 0.
So y
Yeah,
can
yeah.
be anything. So y is the independent vector. So the nullity is
Hmm.
1. Right? And the basis will be 0, 1, 0.
Okay.
Right? So now we have obtained
Hmm.
one basis for lambda equal to 1. Okay. So what we will do, now we want
Hmm.
to express this matrix which is in the lower triangle. We want to express this into an upper triangular matrix. We want to find out a basis with respect to which it can be written as a upper triangular matrix. Okay. So we have one vector. Now, but this lambda equal to 1 has algebraic multiplicity equal to 2. So it cannot be converted into a diagonalizable. It's not a diagonalizable matrix. Okay, that is clear because the algebraic multiplicity is not equal to geometric multiplicity, right? So it is not a diagonalizable matrix. But what we can do, we can convert it into an upper triangular matrix. How? So for that, let's say we have find out one basis, one eigenvector. Okay, we have find out one eigenvector for lambda equal to 1. Now what do? We will consider a basis that it starts with this eigenvector 0 1 0. Okay, so we complete this basis. So how do we complete a basis? How do we complete a linear independent set? By adding more bases, by adding more vectors to it, so that the set becomes maximal independent. Okay. In particular, we need to add two vectors in this case because we have just one vector. We need to add two more vectors in order to form a basis of R3. Is that clear? And what vector do we add? That we
One
take
zero
the
zero 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 one.
in this case we
One
take some
one.
uh,
Hello.
Excuse ma'am, sir.
yeah.
The second vector will be the for the eigenvalue 3, right? So only we need one vector to extend this to a base of R3.
No, no. So what I'm doing as of now, I am just starting with the first eigenvalue and I'm looking at the eigenvector of it. I am not looking at the other eigenvector for the other eigenvalue. Okay. So the first vector I'm taking, can you
Okay.
repeat that?
Understood. Understood.
Yeah. So now I'm completing this set by adding two more vectors which are independent to the first vector. Okay. So this is how I have obtained a new set of bases. Okay. So this
Here
was a
I
matrix
have a doubt.
representation with respect to canonical.
Excuse me.
Yeah.
You're considering a basis B is there, right? D actually it is in a span of R3, so we can take any basis, right? Like which is
Yeah.
independent. Am I right?
Yes. Yes. Yes.
So it should be. It can be like first is 0 1 0. That is initially we got the null. Next I can take it like 1 1 0 also, right? Because it is in
Yeah.
a
Yeah. You
span.
can take 1 1 0 also.
Yeah. That
Yeah. There
was
is no problem with that.
confirmed. Okay.
Yeah.
Okay.
Yeah. You can extend it anyway as long as
Yeah.
this serves as a basis.
But it should be linearly
I'm
independent.
making a yeah. Yeah. I'm making a specific choice in this case.
Okay, sir. Okay, sir.
And why do I do so? Because it is the simplest choice that I can think of. That's why I'm doing so, to save the computation
This
for.
one we can derive currently.
Sorry.
That is the least point we can currently consider, right?
Yes, 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 yes.
Okay. And one small query, sir. This eigenvectors is there, right?
Yeah.
For that, this is like on 3 cross 3 matrix, right? So suppose if there
Right.
is no there is no it is linearly independent, like, and we have many vectors like 4 cross 4 matrix or like that one. So suppose there is no
Mhm.
upper triangular or lower triangular, then we have to find the eigenvectors, like in roots we have to find that values, right?
Okay.
No, my question is like that solving that we have to use that synthetic division method, or is like that is very lengthy actually. Like you have to keep on row multiplying then again. So
No, no, I'm not. I lost you. What are you talking about?
that eigen values are there, right? That is exactly, if you see, means it is a roots, right?
Yeah, it's a root of a characteristic polynomial, right?
Uh-huh. Here, because here it is in upper triangular, so we can directly figure out the roots. Suppose in
Lower
exam, if
triangular. Yes. Hmm.
there is no like upper triangular, then we have to configure the root, right? Like determinant we have to find then again.
Right,
So
right, right, right.
that division method is like that upper upper division method, something is there, right? Like that is very lengthy, sir. That is the reason I'm saying. Like if it is more matrix, so
Yeah,
in
yeah,
a short of.
you cannot even calculate algebraically if the polynomial has degree more than or equal to 5. So that is not
Hmm.
possible. So there is a theorem in mathematics. So it is algebraically hard to solve a polynomial to find roots of that. So that's a completely different domain of problem. But what do we do? We have
Okay.
some numerical methods to approximate the roots of a polynomial. That's what goes into
Hmm.
the programming part of it. So you insert a polynomial, then it can approximate the roots of that using some multivariable calculus or
Okay.
numerical analysis on that polynomial.
What
So that's a
what
different
you
thing. But
call?
you won't be getting those things in your exam, so you don't need to worry about
Okay,
that.
okay, sir. No problem, sir. You can continue, sir. No, I just want to confirm, sir. No problem.
Yeah. Uh, so right. So you can extend the basis, starting with the basis, starting with the eigenvector for lambda equal to 1, like this. So I'm extending it in this particular way. So now what do? I need to, so because this matrix A is given with respect to the canonical basis, okay, E1, E2, E3. Now I need to I need to perform a change of basis and I need to write down this matrix A with respect to this new basis. Okay. So how do I do that? So for that, I need to multiply by a matrix P and P inverse. All right. What does P do? So P matrix has columns given by the new basis. Okay. So that's what the P matrix is, and P and this is nothing but the inverse, which I multiply from the right. So this is from the last session yesterday that we discussed. So it is coming directly from that. Now I can perform this change of basis matrix, and if you multiply it in this order, so you will end up getting with a matrix which is of this form. So this matrix AB is the matrix representation of the same matrix with respect to the new basis B. Okay. Now as you can see that the first column of this new matrix becomes 1 and the other entries in that is 0. So it is becoming upper triangular with respect to the first column. But so now what do we do? So we leave out the first column because first column is done. First row also we remove. We leave out the first row. So we consider this block. Now in this case, the block itself is a diagonal matrix. So we don't need to do anything more to that. But it may happen that it need not to be a diagonal, or there might be some non-zero entry over here. Okay. So in that case, you consider this block and then you repeat this whole process. Okay. So now it will be a block with with a smaller order. Okay. So in this case it is 2 cross 2. So now you again find out the eigenvalues of this block, which is 1 3. Eigenvector for lambda equal to 1, you will find out 1 0, and eigenvector for lambda equal to 3, you will find out 0 1. Okay. So what does this mean? That the so this is already a diagonal matrix, so we don't need to diagonalize it further. Okay, so it is perfect. You cannot perform a upper triangulation of this thing. That means the basis that we have chosen earlier, that means B, is sufficient, is working. Okay. So in some cases when, like, suppose you have some non-zero entry over at this point, so then you need to perform this upper triangulation or non-zero entry at both of these ends. So then you need to perform this upper triangulation method again, and you will obtain some new basis uh, in this case, and then you need to perform the change. Okay, so the basis with respect to what we have obtained, that is sufficient. So this basis, if is the basis with respect to A has a upper triangulation, A is a upper triangular matrix. Okay, the matrix representation is upper triangular. So that is what this example says. Okay, so in general also, if you have a linear operator T, and there so that then there exists a basis with respect to which the matrix T is upper triangular. Okay, so the operator is going to be from T from Fn to Fn. So then there is a basis with respect to which the matrix A T is upper triangular. Now, so there is one fact that I'm using in this case to prove this theorem. The fact is that you will always have an eigenvalue of a given matrix. Okay, matrix representation, you will always find an eigenvalue. Now, why is that the case? That is possible because I can consider the complex vector spaces also. The vector spaces need not to be real vector spaces. You can always find out a solution, a root of a polynomial uh, of a complex uh, coefficient. Okay, that's why I can have this theorem. So what I'm saying is that you can have an example like this. You can have a matrix like this: 0, 1, 1, 0, or minus 1, 1, 0. You can have a matrix like this. Okay,
It will be same, right?
and huh?
If you do eigenvalues will be your if you want that eigenvectors, it will be same itself, right? A
No.
minus lambda.
What is the polynomial? So the polynomial in this case is determinant of minus lambda 1 minus 1, which is lambda square plus 1, right? Now, what is lambda square plus 1? So does this have any real solution?
No, it will be similar.
It will be
Complex
Similar. Lambda is equal
solution.
to
no, lambda equal to 0 is not a solution.
Lambda will be plus or minus I.
Yeah, so it does not have any real
plus or minus.
solution.
Yeah,
It
plus or
does not
minus.
have any real solution.
Yeah.
Okay, so what I'm saying is that it does not have any real solution. It can have a complex solution. So, this theorem makes sense when you are working with an operator which is from complex Cn to Cn. Okay, not Rn to Rn. In Rn to Rn, there can be matrices which does not have any eigenvalue. So the proof of this theorem based on the fact that the uh, the matrix always have an eigenvalue, but there can be cases when the matrix does not even have an eigenvalue, which is like this. For example, simplicity. This is the simplest example that you can think of. So we've always be considering f to be c while writing this theorem. That is what my point is. Okay. So if you consider your field to be c complex numbers, then you always have an operator given on that. Then you can always find out a basis with respect to which the matrix is of upper triangular. You can always convert your matrix to be an upper triangle. That matrix need not to be diagonalizable. Okay, the matrix representation need not to be diagonalizable. The operator need not to be a diagonalizable operator. But you can always find out a basis such that it will be upper triangular uh, matrix. Okay, so that is the case. Right. Okay, so now let's look at this. Uh, so now from this operator, okay, suppose you have an operator T from Cn to Cn, and you can find out a basis. Suppose you have find out a basis with respect to which the representation, matrix representation is upper triangular. In particular, you will have something like this. The matrix representation will be of something like this, where the diagonal will correspond to the eigenvalues of the matrix T. Okay, so uh, last in the last session yesterday we saw that the eigenvalues are independent of the matrix representation. Okay, we saw in the last session. So whatever change of basis you do will not change the eigenvalues of the operator. Okay, so eigenvalues will remain same. That is the first thing. So the diagonal of this matrix will be the eigenvalues, and you will have an upper triangular matrix with respect to this by the above theorem. So now what is the algebraic multiplicity? Algebraic multiplicity is nothing but the number of lambda eigenvalue repeats itself. Okay. So that's the algebraic multiplicity of lambda, and geometric multiplicity is nothing but the dimension of this space, which is the dimension, which is the nothing but the nullity of this empty minus lambda I. Okay. Now, how many times? Now, if you look at this matrix empty minus lambda I, if you look at this matrix empty minus lambda I, if you look at the diagonal of empty minus lambda I, so look at the diagonal of null space of empty minus lambda I, what you will find out that number of zeros in the in diagonal of this will be same as the algebraic multiplicity of lambda, right? number of zero that will appear in this matrix will be same as the algebraic multiplicity of lambda. So whatever matrix you will get over here, okay, the upper triangular matrix. So what does it say? Uh, so it says that now you need to comment about the n number of independent variables that you can obtain in this matrix. Okay, that you can obtain in this matrix. So suppose if these column this row is non-zero and you have obtained zero over here in the difference, and you have obtained a zero over here, right? So what does it say? That only the first vector, first variable will be the independent one. So in that case, uh, yeah. So in that case, what you will the relation that you will get is the nullity. So this number of zero, which is equal to the null, which is equal to the algebraic multiplicity of lambda. So the geometric multiplicity, that means the nullity, the number of independent variables, will always be less than or equal to the algebraic multiplicity. It cannot go beyond the algebraic multiplicity. So this is the relation that you will get in this case. Okay. Now, so once you have a matrix, once you have an operator from Fn to Fn, and you can find out a basis, and you have written down the matrix representation with respect to a basis, so that you get an upper triangular matrix like this. So what is the trace of this matrix? So trace of a matrix is nothing but the sum of the diagonal entries. Okay. So what is the diagonal entries in this case? The diagonal entries are the uh, diagonal entry of this matrix representation is the sum of all of the eigenvalues. So it is sum of all eigenvalues of T. All right. Similarly, the determinant, because it's upper triangular matrix, the determinant is nothing but product of all of the eigenvalues, all the eigenvalues. So it is product of all eigenvalues of T. All right. Now you may ask to me
This
that,
it is diagonal matrix, right?
sorry.
This can you explain that? Sorry, can you repeat what is this trace? Trace is diagonal matrix. So the
No,
sum
no,
of all
trace
eigenvalues
is
of
sum
T.
of diagonal entries.
Sorry.
Sum of diagonal entries. Okay, so let me write down here. So trace of a matrix is sum of diagonal entries. Okay, trace of a matrix is sum of diagonal entries. So in this case, for empty, the diagonal entries are the eigenvalues. So if you sum them up, you will get the sum of eigenvalues, which is nothing but the trace of empty. Now, you may ask that is this trace trace of an operator? Is the trace of the operator is independent of the choice of matrix representation or not? Okay, because in this case, it looks like it is dependent on the choice of the matrix representation, right? But the answer is no, it is not dependent on the matrix representation. It is completely, it's a property of the operator. So how do we prove that? We know that. How did we obtain empty? We obtain empty. So if you have two matrix representation, so what is the relation between those two matrix representation? You can perform a change of basis and you can obtain one from another. Okay. So when I say change of basis, that means I multiply by a P matrix and its inverse from the left, and I will get the other matrix. So what I need to prove is that trace of A should be equal to trace of PAP inverse, where P is the change of basis matrix. Okay. Now this is same as proving that if I can prove that trace of AB is same as trace of BA. Obviously, in this case, I'm assuming that all of my metrics are square metrics. Okay, A and B are square metrics. So for A n cross n and B n cross n. Okay, so if I have this relation, then I can easily prove this relation. And once I have this relation, then I can prove that trace is a property of operator, not a property of the matrix representation. All right. So how do we prove this? Trace of AB is equal to trace of BA. So I will take a simplest case when n is equal to 2 for 2 cross 2 matrices. Okay. Suppose you have two matrices, A, which is A, B, C, D, and B, which is E, F, G, H. If you take the product of that, you will get. We just only need to focus on the diagonal entries. We don't need to look at the other entries. So diagonal entries, how do we obtain 1 1? So 1 1 is first row, first column. All right. First row, first column, you will get this entry. Second diagonal entry, second row, second column. All right. Second row, second column, same result. Right. So as you can see that B diagonal entries of AB is same as diagonal entries of B. So their sum will also be same. That means trace of that means we have proved that trace of AB is same as trace of B. Now in generality also you can perform
Excuse
the
me,
similar
sir.
argument. Yeah.
But there in the AB, the 11A11 is AE plus BG. And
Hmm.
for the BA, the A11 is EA plus FB. How it is same?
Oh right. I must have done some mistake. So
For the BA, it would be EA plus FC.
FC, right? Should be FC, um, FC, and then it should be uh,
For
BG
the
in the
second
end.
one in the
Yes, because
GC.
second column. So BG HD. Now it is fine, right?
Got it, sir.
Yeah, thanks for pointing that out. Right. So if you look at the sum, the sum will be equal. All right. So you can generalize this argument, or you can prove by induction also. Uh, the however way you like, but in generality also the same result holds true. Okay. For if you take n cross n matrices, then also the result holds true. Okay. So once you have this result, now you can prove this for the above case. So trace of A is equal to trace of P inverse. So trace of okay. So let's start with trace of P inverse. This will be equal to trace of P inverse A. Okay. So what I've done, I have taken this and I have uh, performed this property star by star. Okay. So now we know that P inverse is identity matrix, and identity times anything is equal to the same matrix itself. So since these two are true, we get that trace is equal to A. All right. Okay. So the trace of operator is a property of the operator, not the property of the matrix representation. So that is clear now. Now let's come back to determinant also. So determinant of MT is the product of eigenvalues, as you can see in this case. And again, the same argument holds true for determinant also. Determinant of an operator, you can say, is property of the operator, not the property of the matrix representation. Right. So we already know that determinant is distributes in the product. Okay. So what do we know? We need to say that determinant of P inverse is equal to, it will be determinant of P times determinant of A times determinant of P inverse. Okay. Now what is determinant of P inverse? It is same as, now these are three real numbers, so you can club them. So you will get determinant of P times determinant of P inverse times determinant of A. Now this thing is equal to 1, because what is determinant of P inverse? It is nothing but 1 over determinant of. So it will get cancels out and you will get 1. So it is equal to determinant of A. Okay. All right. Yeah. Any question till this point? All right. Okay, so next topic is near diagonal form. So we have noticed that not every matrix is diagonalizable. Okay. So what we can do, we can either find out a basis with respect to which it can become an upper triangular matrix. Okay. Or what we can do, we can find out a near diagonal form. What is a near diagonal form? Near diagonal form is that it has lesser entry. It has diagonal entries and it has entries near to the diagonal entries. Okay. So it is like a thick diagonal, you have non-zero entries, and rest of the entries which is outside the thick diagonal, they are non-zero. Okay. So for example, suppose this is a matrix, it is an upper triangular matrix, but it has entry, sorry, it's a lower triangular matrix. It has entry in the diagonal, it has entry in the lower diagonal, and at the bottom right, bottom left corner. So how do we want to convert it into, so that it has some diagonal entries and it can have some lower diagonal entries also. Can we get rid of this corner entry? So in some sense, okay. So we want to find out a near diagonal form. Now, what do we have? What we have noticed that this matrix, while calculating the eigenvalues and eigenvectors correspond to each eigenvalue, we notice that what are the eigenvalues of this? First of all, uh, the eigenvalues are 1, 1, 3, because it's an upper triangular matrix. It's a sorry lower triangular matrix. The diagonal entries are 1, 1, 3. Okay. Now for lambda equal to 1, what is the diagonal? What is the eigenvector? I have written down 0, 1, minus 2, but let's find out. So yeah. So let's find out the eigenvector for lambda equal to 1. That means you need to calculate the null space of A minus I. What is your A? A is this A minus I. What it will be? It will be null space of 0, 0, 2, 1, 1, 1, 0, 0, 0. All right. Now, what is the null space? Can anyone tell me what's the null space? You also need to perform one more raw proof operation. So this is equivalent to finding out null space of 0, 0, 0, 1, 0, 0, 0, 1, 2. Right now, can you guys tell me what is the null
X
space?
equal to 0.
X equal to 0. That means 0 in the first
0
quadrant.
minus 2 1.
0 minus 2, 1. No. There is one independent vector. So either you take z to be independent, so then you can write y in terms of z. So it will be minus 2z, z, and z is the independent variable. So what will be the basis then? It is 0, minus 2, 1. Right? What is the basis of this null space? It is minus 0, minus 2, 1. So that is what I've written over here, right? Is this clear? How did I calculate this eigenvector? Right. Now let's calculate the same for eigenvalue 2. Okay. So for eigenvector,
Confirmation. Hello.
yeah,
Eigen vector is there, right? You're just multiplying that whole null vector into x, right? X, Y, Z, right? In down models. If I'm not wrong, then again computing it, right?
yes, 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 yes.
Okay. Okay.
Yeah, and you multiply x, y, z and equate it to zero vector, and then you will get some relation. So x will be 0, and y plus 2z is equal to 0. So that means either you can write y in terms of z or z in terms of y. So there will be one independent vector. So I choose to write y in terms of z. So I will get minus 2z. All right. So eigenvector for lambda equal to 2. Right. So it will be just null space of a minus 2I, which is same as null space of what's the vector? Minus 1, minus 1, 1, 1, 1, and 1, 0, 0, 0. All right. Because my original matrix was this. So if you subtract 2 from the diagonal, and this is what you will get. Now, this is
X equal to 0, Y equal to 0.
no, just a second. There is a problem with this. It has rank 3.
X
Cannot
is
have a
equal to
rank.
0, Y is equal to Z is also 0, right? For this lambda equal to 2.
Yeah, it cannot have a rank 3. There's a problem with that.
I have a feeling that 2 is not an eigenvalue, but
Lambda is 3.
Yeah, I think lambda 3 is the eigenvalue, right? Yeah,
1
lambda
has an
3 is the
algebraic
eigenvalue. Yeah,
value.
somehow I wrote 3, 2 over here. So it's 3, not 2. Yeah, so it is 0. Yeah, now it is all good.
For
So it is
the for the yeah.
2. Yeah. Okay, so yeah, I need to perform some row operations in order to convert it into the echelon form. So let's keep this to be minus 2, and then minus 1 or 1, let's say, and then we will subtract it from the second row. So we'll get 0, minus 2. So let's make it 1, and then 0, and then 0, and then 0. So it will be just z. So it is 0, 0, z. Z is in R. That means the basis would be 0, 0, 1. Okay, this is the basis. Okay, so eigenvector we have find out for lambda equal to 0 and lambda equal to 1. So notice that this set of these two vectors, they do not span the whole R3. Obviously, because they are independent, but they do not span the whole R3. So it is not a basis. So we need to we need to complete this set of bases. Okay. So how do we complete this? So we need to add one more vector to it so that it becomes a basis of R3. Okay. And then with respect to this, we will write down the new matrix representation of this operator T so that it will have some near diagonal form. Okay, so let's do it. So let's add one more vector. So because as you can see that it has third coordinate to be non-zero, second coordinate is also non-zero. So we need to add one more vector which has first coordinate non-zero, and then we are done. So that's what I do. I add the simplest vector which with the first coordinate non-zero. So this is the basis that I will get. Clearly, this is the basis of R3. Now we need to represent our matrix. Now the order matters. So I have added my vector, the new vector in the first at the first place. Okay. So the matrix representation will be with respect to this order of basis, or this order of vectors. Okay. Now let's represent this matrix P. So first, how will I? So I need to write down P
Uh,
with respect to B.
Excuse me.
Yeah.
For the previous one, when we are finding that null, right? So minus 2, minus 1, 1, minus 0, minus 2, 1, 0, 0, 0. Yeah. Here we have to do that in row RR. We have to reduce it again.
Yeah, RREF, yes.
We have to reduce it, or directly we can compute and directly we can't do that.
You can do it either way. Reducing to RREF is simpler. It doesn't leave any more competition to you.
Here you did R R2 minus 3 R1.
R2
No,
minus.
how is it computed here? Like it is R2 minus
No,
3
first
R2.
I divided the first row. I divided the first row by -2. I get this row, right?
Okay. Okay.
And then I removed what I did. I then R2 minus R1. So then I removed this one,
Okay.
R2 minus
Okay.
R1, and then I divided R2 by -2. So that's
Okay.
so I got this. So three row operation till now, and
Okay. Okay.
then I perform R3 minus R1. Then I got 1 0 1 0, and then I perform R3 minus R2. That means
Okay.
I perform 5 row operations to obtain this matrix to this. I've not
Okay.
shown all the operation, but this is
Sure.
what I did. Okay. Right.
Or
So now we need.
alternatively, we can visit the original matrix and see that the third column is 003. So only the diagonal entry is non-zero and the rest of the column is zeros. So we can use the trick and say that 001 is our vector. That also is there. Just the trick from week 7 that the professor had mentioned, that
Yeah.
we don't need
Understood.
to calculate.
I got your ideas. And that is also one of the you can if you can directly find out the vector, that is good enough for you. But then there will you need to verify whether whatever matrix, whatever vector you have find out, whether that's correct or not. So just please verify whenever you find out with such tricks, okay, to be just sure that that is correct. Otherwise, you can always use the method to exact method to find out the vectors. All right. So now we need to find out the matrix, the matrix representation with respect to this new basis. We already have one representation. So let me write down that in the middle. What was that? 100. Okay, so this I already had. Now this is with respect to the canonical basis. Now I want something with respect to this. So I need to multiply it with P matrix. Now what is this P matrix? P matrix will be the columns. These bases become the column of this P matrix. So it is 1 0 0, 0 minus to 1, 0 0 1. Right. On the left, yeah. Mm, right. On the left, I need to multiply the inverse of this, P inverse. So it is 1 0 0, 0 minus 2 0, 0 1 1, inverse of that. Okay, inverse of this. So this is P inverse. So now let's first multiply the matrix A with P. So what will you get?
It
You
should
will
be
get,
0 to minus 1, right?
sorry, which one?
Your P inverse should be 100 0 to 0 minus 2 1, then again 0 0 1, right? For P
No, I've
inverse.
not find out the inverse of it yet.
Okay.
Yeah, I've just written down a minus 1. I will calculate the inverse. So it is 1 0 0. The second row would be 1 0 0 and then 1 minus 2 0. Third row would be, is that correct?
I have one doubt in this. I didn't understood this actually. That trace of B is there, right? So P inverse and P, why it is similar? It should be different, right? If it is
No,
P
P
inverse.
inverse. I've not calculated the inverse here. That's what I'm saying.
Okay, what we
I
should
have not
do?
calculated inverse of this. I've written down inverse of top of it, not calculated.
Okay.
I will calculate now. So what will be the inverse of P? So what is the determinant of it first? Let's calculate that. So it is uh, minus 2, 1 over minus 2 will I will divide by 1 over minus 2. Now what's the adjoint of this? So for adjoint we need to find out the coefficient matrix. Okay, cofactor matrix. So what is the cofactor matrix? And then we will transpose that. So cofactor matrix is for first entry, the cofactor is minus 2. For second entry, the cofactor is 0. Third entry, the cofactor is 0. Fourth entry, for the 2 1 entry, the cofactor is 0. For 2 2 entry, it is minus 1. Sorry, it is 1 just. For the 2 3 entry, it is minus 1. For 3 1 entry, it is 0. For 3 2 entry, it is again 0. For 3 3 entry, it is minus 2. All right, now we need to do the
Sir, for
transpose of this.
sir,
Yeah,
for 2 3, it will be 1, not -1. I think
2 3.
2 3.
No, it is 1, right? Sorry, yeah, it is 1. Hmm. Thanks. Not minus 1. No, no,
Sir, I
it
didn't.
will be minus 1. Because 2 plus 3. It is minus 1 to the power 2 plus 3. So it is minus 1 factor will be there,
Oh, okay, okay.
right? Yeah, Amit.
Yeah, I didn't understood this. How you did like just now you did that. I didn't understood this.
Inverse of a matrix. We have talked about this in some of the lecture. We have already seen this inverse of a matrix.
Okay.
Yeah. You recall to that how do we calculate inverse of matrix using adjoint? All right. So this is the adjoint that I have calculated. And now we need to take the transpose of this. Sorry, this is the cofactor matrix. Now we need to take the adjoint of this. So sorry, this is the cofactor matrix. I need to take the transpose of it to calculate to find out the adjoint of it. So I will get 2 0 0 0 1 minus 1 0 0 minus 2. All right. Now we divide by minus half also. So we'll get 1 over here minus minus 1 over minus this over here, 1 over here minus half over here. Sorry, plus half. 1 0 0
Um,
1 minus 2.
excuse me.
Yeah.
When you wrote it without multiplying with the determinant,
Hmm.
we had those numbers in the matrix over there. So I'm just talking about diagonal entry 2 2 onwards. What we had from 2 2 was, I think we had 1 on 2 2, and then we had 0 on 2 3, and then we had another 1, or was it -1? There was -1 on 3 2, and I think there was -2 on 3 3. So if we
Yes.
look at those four numbers alone, it seems
Hmm.
like that is just what we do for the 2 cross 2 matrix. If we look at P, we look at P above, then we have a 2 cross 2 matrix saying -2 0 1 1, and we do the inverse of that. So -2 will go into the bottom right, 1 will come in its place, and the sign
Yeah,
of
yeah.
1 and 0 will change.
Right, right,
And
right.
so that small matrix, if we invert it, that is
Yeah.
forming the four elements of the actual bigger inverse. And that
Yes.
one over there does not seem to be involved in that too much. I think this is something block matrix, something that the professor had mentioned earlier. Is that right?
Yeah, this is a block matrix. That is true, and it is because of this spatial, because the other entries are zero except this entry is one. Other entries are zero. That's why only working with this block is sufficient in this particular case. When you have such situation that this column, this row is 0 0, so in that case you can just look at this block.
And then, of course, we make sure to multiply with the inverse of the determinant to close out the operations.
Yeah.
Okay. So one easy way of calculating the inverse is that is also a valid method of doing things.
Yeah, but you need to have matrix in this particular form, otherwise you cannot.
Right, right. We need that condition.
Yeah, so it is like doing this or doing that. Because of this simple matrix, I could have calculated the inverse quickly. Otherwise, it could have been hectic task for me also. Okay, so now just multiply. So we will get 100, and then yeah. So it will be half. Half plus 1, so it is 3 by 2. Minus 1. Sorry, this. Yeah, so it will be 0.
3.
Yeah, so we have, yeah, so in some sense, we have reduced the matrix up to some point, or have we not? Yeah, so we have obtained one more zero entry over here by changing the basis. Yeah, so it is mostly the diagonal entries that are there, except these two entries. So we have gotten some better matrix. It also depends on the choice of basis that you take in the first entry. If you have taken some other choice of the vector, which is independent from the rest of the two, so then you might have end up getting something which is more closer to the diagonal matrix. Okay. So yeah, so we have obtained a matrix representation of T, which is better than the previous one, and it is closer to diagonal. So such forms are called near diagonal forms, where the matrix is not diagonalizable, but you can add bases to the collection of eigenvectors to get a new set of bases, and then you can express your matrix with respect to that basis. Okay. All right. Now,
Excuse me.
yeah.
Regarding our choice of this third vector, in the
Uh-huh.
lecture, professor had said that there is some clever way of doing it, so you can get very close to the diagonal, as in you will
Okay.
have only one more non-zero entry and everything else will be zero. So what is
Okay.
that clever method exactly? I think he didn't elaborate over there. Could you shed some light on it?
Yeah, I don't know immediately what should be the clever method. Let me figure it out, and then I will let you know.
And maybe
Um,
I'll find the timestamp of the lecture. If you just give me a minute, I'll just
yeah,
tell you where exactly he brought it up. Just give me a minute, I'll get back to you.
yeah, sure, sure.
Right. So it is in the near diagonal matrices lecture at
Mhm.
minute 100, roughly minute 115, 1 minute 15 seconds and all. That was the point. Maybe you can look it up.
Yeah, right. Yes, so what you can see in this case is that the second column, all right, the second column is exactly the 0, 1, 0. So if you multiply your uh, eigenvector corresponding to 0, 1, 0, you will get this thing. So second column, third columns are as good as diagonal, except the first column, that is the problematic thing, because we have chosen a such vector uh, which which is creating the problem. So, how to find a better choice of this vector? That is the question. Yeah, I know professor has used -230, but why that choice? That's the question. So, yeah, I need to think about it because it is not immediate to me. Um, how can we have lesser values over here? Because we cannot get 100, so we need to get something which is uh, something like this 1A type thing.
Just out of curiosity, do you have access to the professor?
Access to professor.
Are
Yeah,
you able to meet him personally? Then you can ask him, right? Is that possible?
yeah, yeah. I don't. Yeah, I can figure it out on myself. I will let you know.
Okay. Yeah.
Yeah.
Would be nice to know what method he used exactly because he didn't elaborate on it and left me curious.
No, maybe it is very dependent on the choice of matrix that you are starting with. It's not random. It's yeah. Hmm. He does discuss a very particular choice of extension when you have a one particular choice of case when the all diagonal entities are same and then the off diagonal is BV and the rest is C. In that case, he actually does discuss a particular choice. Uh, but yeah, okay. If I come across a method, then I will let you know. All right. Okay, so this is the last topic of today's discussion: the circular convolutions and circulant matrices. Yeah. Anything else from this part of the question? Yes, Mani Shankar.
Sir, is there any standard ki up to what extent we will call it as a near diagonal matrix?
No, as long as it has off as lesser as closest to the diagonal, then it is near diagonal matrix. So what it means, it is uh, that means the off diagonal entries should be zero, as many as you can get. That's what near diagonal matrix is.
Okay, sir.
Yeah. Okay. So circular convolutions and what is the circulant matrix? So it basically based on this example that you might have seen already in the lecture. So this is one of the application in signal processing. Okay, where you have this FIR filter, uh, impulse filter, finite impulse filter. So where there are input signal coming in from the one end, and then you on the receiving end you have the output signal coming up. In between, there is this filter which has some impulses, and this process is quite linear actually. The output signal linearly depends on the input signal and the impulse factor that it has in between in the filter. So, in particular, how do we get the signal? It is like this in this particular case because there are only two impulse factors are there. So, we will have this type of outcome. Xn n minus 1 should be xn minus 1. All right. We will have this type of outcome. So, in particular, if you want to find out the output signal that comes out first, it will be x naught h naught. The second output signal is in particular this x1 h naught x naught h1, and then the third signal is basically in terms of x2 and x1. All right. Now you can write down this whole input and output because it is coming out in very linear fashion. You can write it down in terms of a matrix multiplication. Okay, y naught, y1, y2 multiplied with this matrix, and then this. Now, what's the speciality about this matrix? If you look at the matrix, it has the all the columns, they are moving in a circular form. Okay, so if you look at knowing the first column is sufficient to form this whole matrix. That's the first point. And why? Because there is a circular path that they are moving. Yeah, there's a shift happening at the vertical shift happening in each column, and then that's how you obtain the second column and the third column. Okay, so such matrix are called the circulant matrix or circular matrix, and there is a specific way to solve them, because solving such matrix or finding out eigenvalues or eigenvectors to this matrix help to simplify uh, representing this matrix in a simpler form, and then hence you get the output in a simpler form. So it is, so this impulse matrix or this matrix corresponding to this filter can be expressed in a simpler terms. Okay, and how to obtain this simpler matrix? By change of basis, in particular by finding out eigenbases and expressing it into the eigen terms, eigenvectors. Okay, and how do we find out the change of basis matrix? By writing down the eigenvectors as the column of the change of basis matrix. Okay, so because this is a circular matrix, there is a specific there is a solution to that, and that solution is very particular. So you just need to know the first column, and once you know the first column, the eigenvalues are nothing but lambda j, c naught plus c1 omega to the power minus j, c2 omega to the power minus 2j, and so on, where omega is the first root or the primitive root of the unity. All right. And the eigenvector corresponding to each lambda j is of this type, where omega is nothing but the primitive nth root of unity. Okay, this is a specific value. And what do I mean by the nth root of unity? So, for example, you have already seen one of the example of root of unity. So, x square plus 1. Okay, sorry. Um, yeah. So, you have already seen x square minus 1, or x square is equal to 1. So, all solution of x uh, square roots of x, square roots of 1. This will be the solution of x square equal to 1. The solution will be plus minus square root of 1. And this is nothing but plus minus 1. Okay, so this is simple case. But when you find out the cube root of 1, okay, then you need to go to the complex roots. Okay, complex cube roots. So 1 will be the one root, but what are the other roots? So the other roots turns out to be e to the power 2 pi I by 3, e to the power 2, e to the power 4 pi I by 3. Okay, this will be the root. And what is this expression? This expression is whenever you have r, whenever you have r I theta, a complex number. In this case, r is equal to 1, so we will not. So this has an Euler expansion. So this is cos theta plus I sine theta. So what does this mean? This simply means that you have a rectangle, you have a circle, a unit circle. Okay, what is a unit circle? Circle of radius 1 in a complex plane. So you have a circle in a complex plane C. This is the origin, and you have a circle in a complex plane like this. All right. So right. So this is 1, and then because you are finding out cube root of unity, so it basically you need to consider an angle. This whole angle is 2 pi. So you need to slice this angle into 3 parts, 3 equal parts. So you will get 2 pi by 3. All right. So this will be 2 pi by 3. In particular, this will be something like, so in particular, this will be 120 degree. And then you will take one more 120 degree. Somewhere here, I guess. What it did. This will be 30, this is 60, and then somewhere here. Yeah. This will be 120 degree. 30 degree lesser from the minus x-axis, minus y-axis. And then you will have this. So what are these points? These points, if you calculate, this is the y-axis, this is the real axis. So this is, what is this point? So look at the, where does it intersect? So what is this point? So any point in this circle has coordinate cos theta, sin theta. All right. So cos theta is the x-axis coordinate, and sin theta is the y coordinate. Right. So how do we calculate this x theta? Why it is cos theta called, why it is sin theta? It is simple trigonometry. If you look at this angle, which is let's say theta, then this is a 90 degree angle. All right. So what is the base? Base is So what is cos theta? Cos theta is, so this, cos theta is the base divided by the hypotenuse. All right. So if it is P, so it is OP, right? And then this is Q, let's say. So base is OQ and OP. So what is base? So base is the coordinate of x-axis coordinate of base is the x-axis coordinate. And what is OP? OP is radius of the circle. Radius is already we assumed it is a unit circle, so it is 1. So OP is 1. So OQ is cos theta. So OQ is cos theta. Similarly, what is sin theta? Sin theta is perpendicular by the hypotenuse. So perpendicular is QP divided by OP. OP is 1. So again, sin theta is QP. So the coordinates will be cos theta, sin theta. Okay. So any point on the unit circle has coordinate cos theta, sin theta. Okay. So now you can have, so this point, which is making an angle of 2 pi by 3. So what it would be? It would be, so that's how I write 2 pi by 3. So this is that 2 pi by 3. And then what is the next angle? It is 4 pi by 3. It is 2 pi plus 2 pi. 2 pi by 3 plus 2 pi by 3. That is 4 pi by 3. So that's the next angle. Okay. So this is, so these will be the unit. So these are the unit cube root of unity. Okay. And they are the complex numbers. Okay. Suppose if you have 4 root of unity. Okay, so you will have, again, you will take the same circle. You will start with the circle. All right. This is your complex plane. You take the circle. All right. And then you have, let's say, 4th root of unity you need to find. So how will you find out? You need to start with this 1. 1 is always the solution. And then you will take 90 degree. Because 4th, so you need to divide 2 pi into 4 equal parts. So it is 90 degree. Then it will be this. next is this, next is this, and then this. Okay, so it is -1 I minus I. All right. So these four will be the coordinates, and you can also express in terms of x to the power 4 equal to 1, so it is 4, and then e to the power 2 pi I by 4, e to the power 3 pi I by 4, uh, sorry, it is already 2 pi, so it is yeah, 2 times this, so it is 4 pi, and then e to the power 6 pi by 4. All right. So what is pi by 2? So this will become pi by 2. This will become pi. This will become 3 pi by 2. So pi by 2, and then this whole angle pi, and then this whole angle, this is which is 3 pi by 2. Okay. So yeah, in particular, you can have in particular, if you have nth root of unity, you need to find out. So then you take a unit circle, you divide that unit circle into equal n parts, and then each of that coordinate will be x. So the simpler way to say, if you have nth root of unity, if you want to find out the nth root of unity, then simpler way to say that the nth root of unity is yeah. So nth root of unity, that is the solution of this equation are 1 1 e to the power, so you can just simply write it in just this 2 pi I k by n. Okay, where is k varies from 0 to n minus 1. Okay, or you can say that it varies from 1 to n, whatever suits you. So it either varies from 1 to n or 0 to 1 minus n. So it will have all the solutions, all the roots. Okay. Now coming back to the circulant matrix. So whenever you have a column, the eigenvalues are nothing but this, the jth entry, the jth eigenvalue is C naught plus C1 omega j minus j, C2 omega 2 minus j, and so on up to n minus j. So what it actually says, it actually says that it is C naught plus, now what is omega? Omega is the first root, primitive root, 2 pi I by n, the first one. So what does this say? This is C1 times e to the power minus 2 pi I by n plus C2 e to the power minus 2. Now it is 2 times 2, so it is 4 pi I. So let me just write 2 in the 2 here, I, and then 2 by n, and so on. So what we are doing, we are writing down all the units, all the roots together, and then multiplying with the column entries respectively. So that will be your eigenvalue. Yeah. Oh, sorry, there is j factor also. So this 2j factor is also there. Yeah. So it is. So it is not just the factor. There is j factor is also there. So yeah. So j is a natural number. I is the complex number and j is the natural number. So don't get confused with too many notations. Okay. Yeah. So this will be the case. So it is not the all roots. I said that. But yeah. But what will happen is that yeah, it will be part of some roots. Okay, this combination. And similarly, for calculating the eigenvector also, you will have this column. Okay. So you just need to keep these two things in your mind while working with circulant matrix. Okay. All right.
Excuse me.
Yeah.
I wanted to get some clarity on the structure of the matrix itself. Would you scroll up, please?
Yeah.
a little bit more.
Right.
Right. So here the convolution we have described, y0 is written as x0, h0. Very clear. But when
Yes.
we see the circulant matrix and multiply it, we get y0 is equal to h0 x0 plus h1 into x2. How is this happening? It's sort of breaking the law of the convolution itself. I was
Yeah,
having
yeah.
some trouble with
Yeah,
this.
this so I must have written down it wrongly. Mm.
No, in fact, there is no other way of writing this. Since it's a 3 cross 3 matrix, how else are we going to do anyway? We have only 3 of these H's. So either we do some trickery somewhere, or if we do it normally, then I am really having trouble seeing how that is working out.
Yeah, I got your point. Yeah, so I think to accommodate this convolution, we need to work with a different matrix. So let me just try. There's a 4 cross 4 matrix. And let's take x3 to be 0. And let's write it like this. And we will have y0, y1, y2, y3 over here. So y0 is h0, x0. Yeah. So idea is that only. So we need to add because we already have given this system, right? We need to find out a matrix which fits this system, right? So so the choice of matrix, you need to be one need to be careful while making the choice of matrix. Okay. So you can think, or you can have some systems. You can have zero zero. You can add some input signal which are zero in between. So that's what we do in order to accommodate this convolution of system. So that's what we are doing here. So
But then we end up with a y3 which is not defined in the original
no,
expression.
no output. So look, output can have some output, right? There can be some output. Y3 can also be an output if you are thinking that there is x3 which is zero basically. So there can be some output y3 also, which can be think of as noise, which you are not expecting, but which can be you think of as a noise. So y3 is also can be defined like this. Y3 is what? Y3 is x3 times h naught plus x2 times h1, right? This is y3. So which will be just x2 times h1. Yeah. So it will be just x2 times h1 in this case.
So
So
we are allowed to increase the length of our input and output
input.
vectors.
Yeah, yeah. Because when you are increasing the input, so you are not adding any new information in the input, right? You're not adding any new information. You are taking x3 to be zero, right? So, uh, so but you expect something as an output to come out when you add the zero signal in the input, so that the original convolution can be original output can be accommodated in the matrix, right? So this will not work as you clearly mentioned. So this will not work. This matrix will not work, but we need to work with 4 cross 4 matrix, which can accommodate this thing. So this will be the correct circular matrix to work with such system.
So I think this is what we need to do with the question number 6 of the graded assignment of week 8.
No,
I
in
was
that
having
case, you don't need to.
deadline is still pending, so I won't. I don't really want to talk about it too much, but I think the
Yeah, yeah.
problem was this only. I was not modifying the metrics appropriately, and therefore I was getting some
No, no, I
problematic
think in that
expression.
case, in that particular example, I don't think so. You need to modify uh, that thing, but yeah.
Maybe you can check that question as well, just to see if the answers are right over there. I posted it on
Yeah,
the
I
GSpace.
know. I saw your comment, and there is a sign problem. So you are correct in that. There is a sign problem in the answers. So when I was making that question, so there was a sign problem. Somehow I missed a sign. So the problem was there. So I checked that, verified that thing. I only created that question, so I know what went wrong in that. So yeah. Okay.
Also, one question about these roots of unity.
Hmm.
Here we are seeing that as long as the root we are calculating is of an even variety, let us say it is second root, fourth root, sixth root, eighth root, then
Yeah.
we are getting two real answers. One is 1 itself and the other is -1. And if we have an odd root of unity, we are getting only one real answer, that is 1 itself, and everything else is complex. That's how it looks based on the geometry.
No, in case of six also, you won't get both real roots. So what is six? So it is like 360 by six. You will get 60-60 degree angle. Oh yeah, in six also you will get right one real, two real roots, right? Because there will be x square factor, so that will always correspond to that. Right. So as long as so whenever you have x square factor, um, yes. Yeah. So let me x to the power n. So let's say you take x to m, right? Even power. So then it is what? It is x minus 1 and x plus 1, right? Now, what is this? This is uh, m root of 1. And then what is this? This is uh, this. So you will always get the complex root in this case. Um, Whereas in this case, yeah, right. Mm, right. Suppose you have what I'm thinking is if m is odd, then you will have minus 1 over here, one of the root, and you will have plus 1 root over here. Okay, so you will have plus 1 from here and minus 1 from here. If m is odd, if m is odd number. But if m is not odd, okay, then in that case, you might have, you might not have, you will have all complex. So what is that case? So let's take something like 4m type. Um, right. So what is 4m? Oh, in 4m case, let's say you have 4m x to the power minus 1. You can think of it as x squared to the power x minus 1, which is and then you can again have here m is odd. Right. So in particular, you have something like this x to the power 2k n minus 1. You can break this into how many factors? Uh, you can break this into one factor and then two factor. So there will be two factor at the end, and then there will be k many factor, k minus one many factor. So you can always break into k minus one many factor, right? So there will be k minus two factors, and then there will be the last will be two many. There will be k minus three factors, and then there will be the last factor will convert into two parts. Right. So there will be how many there are? There are four, for four there is k minus. There are three factors. So for two, there can you can break this into uh, k minus one factors. When I say factor, that means I'm breaking it into r, considering my field is r. Okay, I'm working in r, thinking that my x is a real number. Okay, so that's so it first will be 2k m plus 1 and then x 2k minus 1 m plus 1 so on up to 2x plus 1 and x m minus 1. So how many factor will there be? There will be k many factors like this. Yeah, so it is basically 2 to the power 2, right? So and then 2. See, okay, so it is k plus 1 many factors, right? Yeah, so there are k plus many factors, right? Yes, and in k plus many factors, this will correspond to, and this m will always be odd because of the assumption. So this will be, this will give us minus 1 and this will give us plus 1, right? Yes, so whatever you're saying is correct. Yeah, yeah. Are you there, Tanji?
Yes, I was just looking at your logic. So if m is odd and minus 1 is there, then only minus 1 to the power something odd will give us minus 1 again. Is that
Yeah,
what you're saying?
yeah. So you will have these two factors which will correspond to plus 1 and minus 1, right? So For example, if you take this one, so this is x m to the power 1, right? X m to the power 1. Because we need to equate it to 0. Whole thing will be equated to 0. So this will be x m to the power 1. And then this will be x m to the power minus 1. And now m is odd by our assumption. Okay. So minus 1 will, the only real number whose power is minus 1 is minus 1. And the only real number whose odd power is equal to 1 is plus 1. Uh, so yeah, so we will always have two real roots in case of even. Yeah, whenever you have an even power, you will get two real roots, and then whenever you have odd power, you will have only one real root. Yes. Yeah. First, you need to prove that uh, that given an odd power, you have only one real root. You need to prove that, and then once you know that, you can use that fact to prove that if you have even power, then it will have two real roots, and the proof is this for that. And here I'm using one of the property that these all polynomials does not have any root in R, does not have any real root in R except x equal to 1. Sorry, x equal to minus 1. They do not have any other root than this. Yeah, so I'm using this fact also, which is I don't know whether it's, I think it is hard to prove. It seems easy, but without complex analysis, if you just go algebraically, and yeah, I don't remember now whether it's hard or easy, but I think it is immediate only because of the knowledge we have about real numbers. So okay, yeah. So I hope this is fine. So whatever you observed was correct, and the proof is this. All right. So last topic of
At
today's
least
discussion
the
is
at least the geometry gives us clear intuition.
exactly geometry gives you the clear intuition. Right? But for geometric picture, you need to have proof of that also because that is an intuitive thing. But whenever you have even number, then you need to say that whenever the n is even, then cut. It will always cut x-axis twice. The unit circle will always cut x-axis twice. That you need to argue. Uh, yeah. Or you can argue in this way also. So this seems easier to me. Geometrical way seems, I don't have an immediate argument for that. Hmm, maybe it is immediate. We need to say that it's a multiple of pi. In order to say that it's a multiple of pi, um, if you have even number, okay, let's not go into that. So yeah, stability of systems. So what is an stability of system? So we have already seen powers of a matrices, and you can use uh, powers of matrices of diagonal matrix. You can write down a spatial form it in terms of the diagonal matrix, and you can compute the power of that, and it is easier to work with. Okay, for diagonalizable matrix. Now, one of the application of that is in the stability of, or the find the stable situation of a system, a linear system. Okay, so this linear system could be a model for anything. It could be a model for ranking or reviewing of some movies on Netflix, or it could be some weather data, which has linear dependency. Okay, so suppose you have some of that model, and you have modeled it down in terms of this matrix, where this first stable time, so the system at the stable time t stable time n is this given by this column. Okay, and the evolution form of time n to n plus 1 is given by this relation that you multiply by a, the nth state system, and then you get n plus 1 state column. All right. So in particular, if you have some initial data, that where did you started taking your data from, so then it is nothing but the xn can be written as a to the power n times x naught. Now, what is this a to the power n? If A is diagonalizable matrix, then you can have a simpler way to write down this matrix. And then using this diagonalization, if A is diagonalizable, then you can also predict what will happen, what will be the stable data when n tends to infinity. Okay, so you can find out what will be the stable data in this case. So for example, if it A is diagonalizable, you can always, by a change of basis, you can find out a diagonal representation of it, and then you can write down the e to the power k, which will be just the diagonal entries with the k power on it. Okay, so we say that the system is stable if all these entries, all these diagonal entries, are equal to are less than 1 as n tends to as xn tends to 0. Okay, this xn tends to 0. So this will be correspond to the stable system. Now, this is one of the application of the power of diagonalization. All right. Yeah, we stop today's discussion at this point. Um, and I hope I made some things simpler for you. Okay.
I would request you to look into that matter of how the professor chose that particular vector in
Yeah,
that
yeah, I
particular
will.
question.
I will think about it, and then if I don't think so, there is any trick except in the case that he mentions in the lecture notes. Other than that, I don't think so there is any trick, but if I can find out something, then I will mention. Okay, I will either write it on the I will put it on the group, the Google chat.
Sir,
Yeah.
sir, please shed some more light related on circulant matrix and related basis. Actually, it's not very clear to me.
Yeah, what is your doubt? So whenever you have a circulant matrix, okay, so the eigenvalues are of this type, right? And the eigenvectors will be of this type, correspond to each eigenvalue. And what is this omega? Omega is this complex number, which is 2 pi I by n.
And sir, the eigenvalue, calculating the eigenvalue will be very difficult.
No, why it is difficult? You just need to sum them up, right? What is this? This is sum of this is sum of complex numbers. And there are some relations on complex numbers which you can use to write down this to further solve this, right? There are some relation among the complex numbers.
Okay, sir.
Yeah.
Means for a big matrix, it will be very difficult, but for a
No,
sizable
you don't need
matrix,
to. You
it will
don't
be.
need to find out the so for circular matrix, it is easier because you already know what are the eigenvalues, what are the eigenvectors. You already know what are the values. So it is simple in the case of circular matrix. If you have some other matrix which is not circular, then it is very difficult because you need to compute the determinant, you need to find out the roots of a polynomial, which is not even in complex. It is always, you will always find out roots, but you need to find out roots of that, which is difficult task, right? But in circular, you already know the eigenvalues, you already know the eigenvectors. You just write down, you just fill in these details, right? These each of this detail, you just fill in these details, and you will get the answer. And then further, once you get this, then you solve this. Not solve in the sense that if there is some relation, let's say if you have gamma, sorry, omega is given in terms of omega cube is there. So omega cube, if you get omega cube, then it is 1. Some such relations. Uh, if it is cube root, omega is the cube root, primitive cube root, and it is omega cube is equal to 1. And you have to use those relations to further solve this into simpler form.
Oh, okay, sir. Okay, sir. Then it will be easier.
Yeah, yeah. Okay.
Probably there is some very deep reason why the eigenvectors of any circulant matrix are always the same, not dependent on the entries of the matrix at all.
Because of the because of this, because of the form of this matrix. This matrix has a very special form. Okay. So the eigenvalues itself takes the columns. Okay. The entries from the columns. So the eigenvector uh, becomes independent of, and they become independent of the choice of the numbers and the columns. If yeah, it is all because of the form, that the specific form that it has. Up to this, it's n minus 2, and so on. The C naught will come at the end. It is all because of the spatial form that it has.
And crucially, I think we saw today that the circulant matrix, the way we design it, should not break the law of the convolution that we have designed. We need
No,
to
no.
adjust it
So
accordingly.
it's not the no. So there is so convolution. This is one of the application of the circular matrix. Okay, there are other applications of circular matrix. So it's not because circular matrix are formed from this convolution concept. No, there is a concept of circular matrix. It appears in this setup also. That is what the thing. It's not from this circular matrix comes. Circular matrix is used in this. So circular matrix is an independent. You think of it as an independent notion, and which is used to simplify to understand this physical singular process of this singular processing operation. Okay, so yeah, so and you need to be working with a specific, you need to work with some particular choice of the matrix in order to accommodate the convolution, the outputs that you want. So that's a different thing. That is part of that's a manipulation that you need to do while thinking of this singular processing in terms of a circular matrix. But circular matrix is a mathematical concept. Okay, it does not take motivation. It can have some uh, yeah, it may appear somewhere, but it is independent in itself. So it is not completely based on the convolution. That's what my point is. Okay, thanks everyone for joining and asking questions. And I will get back to you